Okay, so now we're going to go over radiometry and photometry. So radiometry and photometry are different in that they use different units to describe the same thing. So in this table, this will kind of tell you the equivalence relations between the different terms. And we'll go over all of these terms in a second, but I just want to give like a little introduction to what units we are looking at. So let's focus on the radiometry column first. We have radiant energy, radiant power, radiant intensity, irradiance, and radiance. These are all including W, which is watts. So this is a measure of energy, and each of these terms measures energy in a different way. So they all kind of serve a different purpose for measuring how energy is emitted and absorbed and kind of like dispersed throughout the world. Photometry, all of these use lumens, which is just another unit that also describes energy. So I'm going to talk about mostly just the radiometric units, and I'll mention the names for the photometric units, but just know they're pretty much the same. Okay, so let's go over number 1, and this will kind of let us introduce all of the different units and whatnot. So what is the difference between radiant flux / power, radiant intensity, irradiance, and radiance, and how does increasing the distance from the light source affect these values? Okay, so what is radiant energy and flux / power? So radiant energy it's just energy. It's the energy of electromagnetic radiation, and it's measured in units of joules. And radiant flux is this energy, reflected, transmitted, received, whatever, it's energy per unit time. Okay, so joule is kind of like our base, like that's energy, and then radiant flux, also called power, is energy per unit of time. Okay, and how does this change with distance? Okay, well, a light source emits the same amount of energy regardless of how close or far the light source is. So this unit doesn't really take into account distance at all. It's only energy over time. So it does not matter where you are in reference to this energy source. Okay, what is irradiance? So irradiance is the power per unit area incident on a surface point. So we just talked about power. This is the amount of energy emitted, reflected, transmitted, or received per unit time. And irradiance, on the other hand, is the amount of power that is being received on some surface. Okay, and since we're receiving some amount of power, we need to define an area with which we are going to measure the amount of power that is being received, right? So if we have like a very large area and we're measuring the amount of power we're receiving at this large area, that's going to be different than if we have like a very small surface. So that's why irradiance also includes this per unit area part in its measurement. So it will be watts per meter squared. Okay, and how does irradiance change with distance. This one's a little more complicated. So let's think about some energy source. It's emitting some constant amount of power. And as this power kind of moves away from the source, it's being distributed evenly in this, you can think of it like a sphere. It's being distributed along this like larger and larger sphere. And so if you're at some point that is farther away from your energy source, you're only getting some amount of that power, since it's also dispersed all along this much larger sphere. Whereas if you're very close to your energy source, the sphere with which your energy is dispersed on is much smaller, and therefore the amount of energy per one spot is much higher. So we actually have an equation for this depending on your distance from the energy source. So if E is like your intensity, your irradiance at your point 1 meter from your energy source, then you're going to have your power divided by 4 pi, because 4 pi is this area of the sphere. And if you're farther away, let's say at some distance r from your energy source, it's going to be power divided by 4 pi r squared, because 4 pi r squared is the area of your sphere. So it's going to be energy divided by radius squared. Okay, so that all is to say that when you're farther away, your irradiance decreases. So irradiance decreases with distance. Okay, so now we are going to talk about radiant intensity. Radiant intensity is the power per unit solid angle emitted by a point light source. So let's go back a slide and just talk about what a solid angle is. So an angle is defined by the ratio of a subtended arc length on a circle to the radius. So if theta is your angle, it's going to be L, the subtended arc length on a circle, divided by your radius. Okay, and then a solid angle is kind of the 3D equivalent of that idea. So since we're in 3D, we're going to take the ratio of a subtended area on a sphere. So instead of length, it's area, and instead of a circle, it's a sphere, and that's divided by our radius squared. So they're kind of equivalent, but a solid angle would be in 3D, and a sphere has 4 pi steradians. That's like the unit of a solid angle. Okay, so radiant intensity is the power per unit solid angle emitted by a point light source. So keep in mind, this is what is being emitted by a point light source. So this is similar to like radiant flux, since that's a way to measure the amount of energy that is being emitted by a point light source. But the difference here is we have also included this unit solid angle. So it's not like total amount of power emitted per second. Instead, it's the amount of power per unit solid angle emitted by a point light source. And there's some units for that. We have watts over irradiance, and in photometric terms, that's a lumen over irradiance. This also has a name because it's one of the 7 base units, so it's called the candela. But really it's just lumens per irradian. And remember, irradian is our solid angle unit here. Okay, so how does radiant intensity change with distance? Okay, so there's two hints here. One is we are now dividing the flux by solid angle rather than area. So that's one difference. And number two is, does the total solid angle of a sphere change with radius? So let's think about that. Okay, a total solid angle does not change with radius. So if we could just go back to our definition here, we know a sphere always has 4 pi steradians. Okay, so it doesn't change, and therefore our radiant intensity is also not going to change with distance. Since none of these units are going to change with distance, our power doesn't change with distance, neither do our radians. Okay, so the radiance is the power emitted or reflected or transmitted by a surface per unit solid angle per unit projected area. So let's go back to this definition here. So radiant intensity is power per unit solid angle. So we have some amount of power being emitted, and we added this extra unit solid angle term on to kind of get a handle on how much power is being emitted in a specific direction. Now here we've taken the same idea. We have our power per unit solid angle, and we have also added per unit projected area. Okay, and this is to further constrain this kind of like idea of energy being emitted or reflected or transmitted or whatever. So that is also one thing to keep in mind. So surface radiance is just some power that is like coming off or coming to a surface. So it's power with respect to some surface, and radiant intensity is power that's being emitted from a light source. They both take in this like per unit solid angle, and then surface radiance also has our per unit projected area. So that means that it's watts per steradian per meter squared. And that is to take into account this kind of idea that as you reflect your energy off of some surface with like a specific area, it's going to kind of expand outwards in this diagram to some projected area. And in order to kind of take that into account, we are also adding on this extra meter squared term. Okay, and this is also called the nit, in case you see that somewhere, but just know that it's watts per steradian meters squared. Okay, and now how does radiance change with distance? Okay, so let me give you a spoiler. It does not change with distance. And then I'll just go over kind of the intuition for this. So say we have some light source and we have two surfaces. We have surface 1 that's of distance 1 from our light source, and we have surface 2 that's of distance r. Well, we saw in a previous slide that irradiance decreases with distance by a factor of r squared. So our irradiance at surface 2 will be E divided by R squared, since our surface 1 has a radiance E. And then our solid angle is also going to decrease by the same factor. And intuitively, you can kind of look at this diagram and see like, oh, like this angle is much smaller than the angle that is right here at the surface that is closer to our light source. And yeah, so as it turns out, it's also going to be W divided by R squared. So both a radiance and solid angle are going to decrease proportionally with distance. And because they both are decreasing, the radiance is going to stay the same. It's not going to change with distance. And this is kind of by design, since this is what we kind of use to describe light in an environment. So we don't really want it to like change with like different like conditions, like, oh, how big is our surface, like where, like how far away is it from the light source, like none of that. Radiance is like going to stay the same with distance, and it's like per specific area. Okay, so that's why we use it to kind of describe our distribution of light in an environment. So like in ray tracing and stuff, we're going to associate some radiance value with our ray, and we're going to like compute radiance using these different radiance values, and this is how we will kind of like understand light in an environment.